This is further stats 1 FS1 from 2024. Let's go ahead and get straight into it. So the variance of x is e of x squared minus e of x all squared. So we first need to work out e of x by doing this times this plus this times this plus this and so on. We get this, and then e of x squared is just all of the x's squared, so this thing squared, and so on. Just replacing those all type then to calculate again. And then, like I said, variance of x is just this one, which is this, take away this one squared, which will give us this here. And that'll be that. Variance of x squared is interesting. That's going to be this formula, but if you put an x squared here, then you need an x to the 4 here and an x squared there. So okay, this is fine. We just need to work out each of the x4 though. So we just do this to the power 4 times this, plus this to the power 4 times this, and so on. Just the same as the e to the x squared one, but with just 4s. And we end up with this, and then we plug that in, and we already know e to the x squared, so we can square that, and we'll take those two things away, and question 1 will be done and dusted. The Poisson question then, so this is going to be x times PO with lambda equal to 2.4, of course. Probably so that there are 3 errors, so we're just looking for probability that x equals exactly 3. You can just type this into a calculator, and you can also type this into a calculator. It's not difficult. This, you could do 0 plus 1 if you really wanted to, sure. After a long holiday, 250 words now, so that's 2.5 times the words that were before. So I'm going to set up a slightly different distribution, where lambda is 2.4 times 2.5, because that's the scale factor, which gets you 6. So the hypothesis will be h0 lambda is 6 and h1 lambda is not 6 using this distribution. And then test using 5%. So all we have to do here is find the critical region. So we just have to test things, just try stuff out until we get numbers less than, I guess, 2.5, because it's a two-tailed thing, because it's just about whether it's changed or not. So we need to go downwards, and p of y is less than or equal to 1 is this. The calculator just told me that. And 2 is this, so that means that 1 less than or equal to 1 is the first thing within 0.025. So that's the critical region on the lower end, and then on the upper end, again, just try stuff. You end up with this, you end up with this. And then because that means that the probability of being bigger or equal to 12 is just 1 minus this, we get this, which is within that 0.025 area for the 2.5%. That means that this is the critical region there. So we've got this one here and this one there on our two ends. A type 1 error is the probability of rejecting h0 when h0 is correct. So what is the chance of rejecting h0 here? Well, you can either reject it through being on this end, or you can reject it through being on this end. So it's just going to be essentially this number plus this number, which I've worked out twice, I guess. And we'll have this there for that. Question 3 then, so it's one of those two-way table test ones. So a very specific part of the book, this. Write down the hypothesis. So this just isn't words. You just say this kind of thing. I believe you have to say either this word or this word. So either association between the two things, or you have to say h0, that the two things are independent or not independent. The mark scheme made it seem like you had to use one of those two words here. But anyway, that's that. And then we need to check one cell to check none of these will be less than 5, because of course when you do the expected to the observed test, the chi-squared test, you can't have any rows less than 5, otherwise you'd have to collapse them. So which one of these will have the lowest expected outcome? Well, it's the one with the lowest total from the row and lowest total from the column, which is this box here. Because when you're doing the expected outcome, you just do this over 240 times this over 240 to find the probability of being in this box, and then just times by 240 to work out the expected value of this, because there are 240 people. So you're just saying the probability of being in this row is this over this, times the probability in this column, which is this over this, times 240, and essentially just one of the 240s cancels, and you end up with this idea, which is this, which is bigger than 5, so you don't cancel it. And the reason this must be the only one we have to check is because, of course, it's got the lowest value from the row and from the column, so it must be the lowest thing when you do this tactic. If you did any of the others, you'd be increasing the number that you'd use, and so it would end up being bigger. So yeah, we don't need to collapse anything because the lowest one is 5.38. And yeah, that's the expected frequency for the cell. And now, if we're doing an actual test, though, they've done the test for us, which is nice. But we do still need to know the degrees of freedom, which is just the number of rows times the number of columns. Take away 1 from each and times them together. So 3 take away 1 times 5 take away 1 is going to be 8. And so we're going to look in the table for the 8th row, because that's our degrees of freedom. And we're going to look all the way across to 1%, which is all the way over here. And we find this. Our test statistic is way bigger than that. So we are going to be rejecting H0 and then maybe writing a sentence about context here, and we'll conclude that there is a relationship between the two things, or association, I guess, to use that word again, between the two things. Anyway, question number 4 then, we repeatedly roll a dice, and then we stop when we get a 3. Now that's a geometric distribution, with probability a sixth, of course, because it's a fair six-sided dice. Now there's a couple of ways of doing this. You could say that P of this, if you want to do it the completely brain-dead way, you just look in the table for the way of getting P of x equals x, and then just say that this is P of x equals 1, plus P of x equals 2, plus P of x equals 3, and then just use those numbers in here. P is a sixth, as we said, and then you just use x as 1, 2, and 3, and you can work out this. Alternatively, just think it through. This here represents dodging a 3 times in a row, and if we want that 3 to actually happen, then it's just 1 minus that, and you'll get this as well. This is just representing the 1 minus p to the n formula, where n is just the number of things. 1 minus p here is 5/6, p is 1/6, and it's just the same thing. But that's just where that comes from. Anyway, if we're estimating a mean, we're pretty much using central limit theorem then. So we're using this idea here, just always write it down, and then mu we can get from the geometric sequence because we've got the table here. That's 1 over p. So 1 over 1/6 is 6. And the variance, which is sigma squared, is going to be 1 minus a sixth over a sixth squared, which is this here. So this will be x to the n with 6 here and 30 over, what is n here, 64, which is, I guess, this. And we're just looking for the probability to be between those two numbers. And we'll just get this as our answer if we type that into a calculator, which you can do. Good. This person wants to check whether the probability is actually less than a sixth. So we're going to do a test. So of course we have to write down our hypotheses. So this will be number 1 and this will be number 2. Of course, we're saying whether it's less than a sixth. So less than, it's a one-tailed test. We repeatedly roll until we get a 3 and it's 16. So what we can do here is we can just say, well, the probability of being more than or equal to 16 is just this. Essentially, you're dodging a 3 15 times. The probability of not getting a 3 is 5/6. You're doing that 15 times in a row. And then you don't care what happens on the 16th row or anything after that, because all that matters is that you've dodged it 15 times in a row. You can get it on the 16th if you want. That represents P of x equals 16. Or you cannot, and you can get it on the 17th and the 18th. It doesn't matter. So it's just about dodging the first 15, which is probability this. That is not within 5% on a one tail, because it's bigger than 5%, so we are not going to reject H0, and then maybe write some context, as we usually do at the end of those sorts of things. Question 5 then, so we've got something about defective things. Clearly we've got an n, and clearly we've got a p, so this is some kind of binomial that we're looking at here. The hypothesis should be with, maybe just write down, of course, the hypotheses. We can see it's greater than, so it's not a two-tailed test again, it's one-tailed like this. And like I said, it's binomial. A is a binomial with n equal to 100, and B is when n equals 80, but we'll get to that later. Firstly, for A, the size of a test, we'll just firstly work out the probability, I guess, of d of 100 being greater than equal to 5. That's equal to, of course, 1 minus that, which is equal to this. The size of a test is just the type 1 error. It's just the same thing. So it's the probability of rejecting H0 when H0 is correct. Now, the probability of rejecting H0 is this, and H0 is correct in our maths here because we've said the probability is 0.03. So this is just the size of the test. This is the type 1 error right here. And so that will do. For B, n equals 80, so our distribution is slightly different, but it's fine. That should say B. I just copy-pasted this and forgot to edit that letter. That should say B. Apologies. So anyway, we've got if D is greater than that, she rejects that. So let's find the probability of that. So that's again 1 minus the probability of less than or equal to 4, which is this. We don't reject it if it's less than or equal to 3. But if it's equal to 4, then we do a thing again. So let's firstly work out the probability of being equal to 4. Which is that. Again, this is all just going in a calculator. I'm not doing anything intelligent. If this is the case, then we do another test, and if d is greater or equal to 1, which is, of course, 1 minus the probability of being less than or equal to 0, which is just equal to 0, which is this, then we reject H0. So we reject H0 if this, or if this with this, because we need this to happen, and then we also need this to happen, so we times these together, and then the size of the test, again, will be the cases in which you reject H0, which is either this case when we're greater than or equal to 5, or this one here when we've done these two things. So add those two things together, and you should end up with this number roughly here. Given that the actual proportion of defective components is this, find the power. So again, the power, by definition, is 1 minus the probability of a type 2 error. That would be one way of thinking about this. And a type 2 error is the opposite of a type 1. It's accepting H0, but it's actually incorrect. Now, we know it's incorrect because it should be 0.6. So I'll just say that again. So type 2 error, accept H0. So accepting H0 means that we're less than or equal to, for A, rejecting H0, as we saw before, was less than or equal to 4, of course, sorry. She rejects if it's greater or equal to 5 in A. So we're going to accept it if we're less than or equal to 4, given P is 0.06. So now we have to do a new binomial with, just maybe name it Y, it doesn't matter, with P is 0.06 and find the probability of being less than or equal to 4, which is this. And so that's, of course, we still need to do 1 minus. So 1 minus that will be the power, which is this right here. So that will be that there. And then find the expected, so this answer, sorry, is this here. Find the expected number of components sampled. So let's think this tactic through here. Now, you are going to sample 80 things no matter what. Because when you sample 80 things, if this, then you stop. If this, then you stop. And if this, then you carry on. But you've sampled 80, so you're going to sample 80. Now, you're going to sample more than that if this. So again, we say probability of this. And again, we're working with a slightly new binomial now, where the binomial has probability 0.06. So probability, with this binomial here, we say the probability z equals 4. That's the only time where we continue. We're going to sample another 80 things. After that, it doesn't matter because we stop the test no matter what. But we are sampling another 80 things if this case. So it's going to be 80 plus 80 times the probability of actually having to do another 80 based on this distribution here, which will give us this answer here. And that will be the answer to this bit down here. And then it says, given that the actual portion is this thing here, I guess, the power is this, suggest which test we should use. Now, what we're supposed to notice here is that the power of both tests is quite similar. This power and this power, pretty similar. And also the size of the tests was also quite similar. This one was also quite close to 0.2. I think I deleted it, but it should also be about 0.2. If the power and the size are both equal, then that doesn't suggest one test is any better than the other, except test number B tests fewer components. It samples fewer components on average. It samples 95 as opposed to the 100 here. And like, imagine if you're sampling actually, in this case, it might do. If your sampling of the component actually breaks the component, maybe you're testing it to its limit where it breaks, then you want to sample less, right? You want to sample fewer of them because then you're wasting fewer components in the manufacturing process and in the sampling process. So we probably want to use test number B here for that reason. Right, finally, some decent maths for question number 6 using some calculus. So buried deep in the formula book is this. You can find it if you look closely enough. But this tells us exactly what we need to do, right? We need to differentiate G not once, but twice, and then just input 1 every time. So let's differentiate it. Let's write it like this so we can actually differentiate. Bit of chain rule, bring the minus a half down, times by minus 3, which makes positive 3 over 2, and then just take away 1 from up there. And then just do it again. Bring this minus 3 over 2 down. That makes minus 9 over 4. But then also times by minus 3, that makes plus 27 over 4. And then bring that power down by another 1. They've been really nice here. They've allowed us to substitute in 1 every time. And they've written brackets that make, the brackets 1 when you put in 1, which makes all of this go away, which is fantastic. So G dashed and G dash dashed of 1 are super easy to calculate. They're just these two numbers here. And then we can just throw those results into here. And we end up with a variance of 6. Now, find the exact value of P less than or equal to 2. A couple of ways you could do this, but the way that I did it was to say that P of X less than or equal to 2 is the same as P of 0 plus P of 1, P of 2. And the whole point, or something that's really nice about probability generating functions, is that when you write them in their kind of polynomial-like form, so it's like something t plus something t squared plus something t cubed and so on, those coefficients just tell you the probability of being a certain number. So the coefficient of t squared tells you the probability of being 2. Or probability or coefficient of t cubed, the probability of being 3. So if we write this like this and then do some binomial expansion using this formula here, I've taken the 4 out and then done 4 to the minus half is a half, because now I've got it in this form here, which allows me to use this formula down there. I'm sure we're all used to this from year 13 regular maths. We end up with this here, just using this formula. Work out all the numbers, don't forget to times by this 1/2, and you get this. And so the probability of x being 0 is a half. The probability of x being 1 is 3/16, because there's a 1 there. And the probability of x being 2 is 27 over 56. So we just need to add those 3 things up. And we'll get to this in the end there. I probably should have written p of x equals 0 and p of x equals 1 here, but whatever, it wouldn't have fitted anyway. Good. And now the next bit here, just be a bit careful. You've got a couple of formulas that you need here that aren't in the book. You've got one that says this. If you've got a function or a distribution is x1 plus x2, your generating distribution is the two generators times together. And you've got another one that says if you're doing a linear transformation, then you do this. Now, you're adding together two things. It's tempting to say here, because x1 and x2 are the same, are the same distribution, that you can just say that's 2 of x1 or whatever, but you can't. They are different distributions, even though they are the same. They're acting differently. They're allowed to act differently to each other. They're different things. So you are going to have to use this one first. Okay, we can times them together first. So my plan here is to kind of times them together first, ignore this plus 1, and make a new function. Maybe in our heads we'll call that function z. And then once you've done that bit, you can then say z is just one lot, or y is just one lot of z plus b, where b is just 1, and you just put a 1 here, so you essentially times it by t to the 1, and then you just have your original function again, because a is just 1. You've combined the functions already, so it's just one lot of the thing. So it's just g of x to the t times t to the 1. But your function is itself these two things times together. I hope that wasn't too confusing, and I explained that okay. Anyway, it becomes really easy from there, right? It's just these two things multiplied together, makes the root go away, you times by t, and it ends up just being this. And then it says state the name of the distribution. So let's look in our table and find which PGF looks most like this. Well, it doesn't really look like any, but it by far and away looks the most like this one, because it's a fraction which doesn't have a power. So we'll try and aim for it to look like this. And the key difference between this and this is that there's a 4 here and there's a 1 there. So let's quarter everything in this fraction to make this. And now we can compare here. If p was a quarter, then that's bang on. And here, if p was a quarter, we could put this in brackets and say it's 1 minus a quarter, and that's fantastic. So yeah, this is a geometric distribution with p being a quarter, and we'll just say that is what it is. Hence or otherwise find this thing. Well, we're of course going to do the hence. If we just add 1 to both sides here, we get this, and then this is just the y. So the question is just p of y greater than 6. And we can use the same idea that we did earlier, which is just for the probability of y greater than 6, you can just use 1 minus p to the power 6. And that's just the cheap way of doing the geometric ones. If you want to do that, otherwise you think it through and you go, well, okay, I have to dodge a quarter, 5 times or 6 times actually if I want to be bigger than 6. So it's 3 quarters to the power 6 because I'm dodging it 6 times in a row before then maybe getting the thing that I want. But in any case, it's just going to be that. And finally, question number 7. Then we're playing a game. It's clearly given us an n and a probability. So this is just a binomial with 20 and a fifth. Just 4 or more means probability of x bigger than or equal to 4, so that's 1 more minus. Probability of less than or equal to 3, type that into a calculator, nothing intelligent there. Find the probability she wins on her 4th prize, so that you could use an intelligent distribution here, but just to add a bit of flair and just think it through a bit. All we really need here is we need her to get 3 prizes somewhere in the first 19 games. So that's going to be 19 choose 3, because she can get them anywhere, times a fifth to power 3, because she's definitely winning 3 times, times 4/5 to power 16, because she's definitely losing that many times. And then after she's definitely got 3 prizes somewhere in the first 19, we need the 20th to be a win. So she gets the 4th win on the 20th go, which is probability 1/5. So we just times by another fifth, and we get this as our answer there. Now these people are playing the game. It plays £1 for every game, but they get £2 if they win the first, 4 if they win the second, 6 if they win the third, I guess, and so on. What is the expected profit of this game then? So let's just call W the number of games won first. And let's say the loss is just n times 1. You're playing n games because it says you're playing n games, and you're losing £1 for every game you play. It doesn't matter whether you win, you still pay £1 every time you play. So the loss is going to be n pounds. The gain is going to be, of course, 2 plus 4 plus 6 plus 8 plus all the way up to 2W, where W is the number of games that they won. Now, that means the profit, therefore, is, of course, going to be this minus this. Now, what about the expected profit? Well, we need to figure out what the expected number of W is, I guess. But first, let's deal with this sum here, because we don't really like the infinite idea here. This is just a sum from 2 to 2W. It's just an arithmetic series, right? Difference 2. And with W terms, because this is like W where W is 1, 2W, W is 1, 2W where W is 2, all the way up to 2W. So that's just W terms. So you've got a formula for that, right? back from A-level maths. We've got this formula here where A is 2, D is also 2, and N is W. So we're going to put that in, and after you do a bit of sorting out, you end up eventually at this. It just essentially becomes W squared plus W. And we have that there. Now again, that's the profit, but that's nothing about the expected profit. For the expected profit, we would need to know the expected amount of W and the expected W squared. Well, that's just E of W and E of W squared. So, okay, triggering some thoughts here. Maybe we can do the same sort of thing that we usually do for E of W and E of W squared. Because actually, when we go all the way back to our binomial, we know what E of the expected value of binomial and the expected value and the variance of a binomial is, right? We know that the expected, I don't know why I put W's, capital W's in here. Don't know why I did that anyway. We know that the expected value from a binomial is just this times this. So the expected number of wins is just NP, right? NP is the mean and the expected number. So the expected number of wins is just N times a fifth, which is a fifth N. And now the variance of W is NP 1 minus P. Now, that's just this, but why would I be finding that out? Well, because remember, I need E of W squared, and I have a formula that links variance with expected of the thing squared. It's just this. So now I can say the expected of a W squared is just add this to both sides, and we end up with this here. So that's fantastic. So now we can say, from our profit, from up here, that the expected profit is the expected of W squared plus the expected of W minus N. And we know all of those things. So we're just going to put all of those things in. We're going to do some tidying up. It's just some basic maths, and we end up with what they wanted us to get here. Now, if Sam chooses N to be 15, find the probability he doesn't make a loss. Well, all we have to do here is work out how many games he has to win to not make a loss. Because he's definitely going to lose £15 if he plays 15 games. So, well, 2 plus 4 plus 6 is £12. So if he wins 3 games, he's making a loss. 12 minus 15 is minus £3. But if he wins 4 games, he's making a gain. So basically, all we need to say is that he needs to win at least 4 games. And the distribution is just when N is 15. So we just need to work out the probability of being greater than 4, which is 1 minus the probability of being less than or equal to 3, which is this thing here. And that's the probability doesn't make a loss. Fantastic. And then this person agrees to play. She'll play until she wins our prizes. Now that is a classic negative binomial. So she's going to play until she wins our prizes. The probability of winning a prize is a fifth. So that's what this setup says. And then it says find in terms of R the expected profit. Now again, you're going to look in the table for our negative binomial and see that the mean is the expected number here is R over P. So basically, what I'm going to say here is that the mean, the expected number of games played, is R over a fifth, which is 5R. So the expected number of games, if you're trying to win R prizes with a property of fifth, the expected number of games that you need to play is 5R. It's because that's the mean here. So it's just 5R. So that means the expected loss is also 5R because you lose £1 every time you play. So she's expected to lose 5R. Now, how much does she win? Well, she's going to win 2 plus 4 plus 6 plus all the way up to 2R. Because she's going to play until she wins our games. So she's going to win this. But we've already seen this before. If you do the same sum, the same arithmetic series sum as we saw before, then you end up with, so the profit is, the expected profit is of course going to be this minus this. And it's expected because although this is known, this is an expected number of games played or loss. Well, from the expected number of games played, it's the expected loss. But this is the sum we've seen before. It just turned out to be R squared plus R. So then we take away the 5R and we end up with the expected profit of this. And that is the whole paper done. Thanks for watching, and I'll see you next time.